Okay, Sten, you can share.
Okay, thank you for that, Hillary. Let's share the presentation, and I will put it in presentation mode. There we go. Yeah, as Hillary said, this is part of the Heliophysics Big Year activities, which each month for 14 months, ending next December, we have a different theme that we're covering that sort of highlights the sun's connection with a variety of sort of human-centered activities. And heliophysics is basically the sort of the omnibus motherhood definition of things that go on inside of the sun, the solar wind, how the sun interacts with the planets, and basically anything that goes on between the center of the sun out to the contact with interstellar space beyond the orbit of, well, the Kuiper Belt and so forth. We like to consider this like a 14-month series of talks starting in October with the annular eclipse. And then in April, we had the total solar eclipse, both of these visible over North America and specifically the continental US. And next December 24th, we'll end the series with, well, that's when the Parker Solar Probe reaches its perihelion, its closest approach to the sun. So that completes this 14-month series of episodes in heliophysics and how it connects with humans. We're in the June month, and the topic is performance art. I didn't select these topics. They were selected by people well above my pay grade. So, you know, we're going to do the best we can to find mathematical connections between the theme that was selected and, well, mathematics that relates in some way to heliophysics and the sun. Performance art, that of course is a variety of things, you know, stage presentations, dance, music, you know, symphonic compositions, and you name it. So it's that kind of topic area. NASA likes to sort of organize, at least for heliophysics and actually for the other divisions as well, its overall exploration questions in terms of sort of like these three big questions. What causes the sun to vary? How do the Earth and the heliosphere respond? And what are the impacts on humanity? Those are the three big questions for heliophysics. We also have questions for astrophysics, questions for planetary science, and questions for Earth science. Same kinds of, you know, three questions that basically, in retrospect, seem to connect the general goals of a diverse collection of resources into some simple to state big questions for each of the disciplines. So, you know, if you're in an elevator going up 5 floors and somebody asks you, what does NASA do with heliophysics? You can rattle off these 3 questions and then basically take on a very blank look to avoid further questions. I'm sorry, that's not what I do, but, you know, it's just, this is like an elevator speech on what, you know, what NASA does in this particular subject area. For education, the heliophysics activation team has decided that we could take the 3 questions and make them more granular so that the sub-questions map into the education standards, the national science standards, a bit more easily. And so these are the 3 sub-questions under each main question. And you can see that, you know, there are connections with the national standards, which are represented in the parenthetical comment, the specific standard that's at play. Well, performance art is what we're going to try to do today. Well, so I decided, because it's something that I know about, I decided one fun thing to look at is music, and in particular, how often the term sun comes up in various popular music that gets released. Um, some of these, I knew off the top of my head, and there's sort of like this partial list here. Some of them are, well, let me take a look at you guys. No, I'd say most of these are before your time, before you were teenagers. But for me, the first one, 1964, that came out when dinosaurs were still ruling the earth. And I remember that song very well on the radio when it came out. Soak Up the Sun, Sheryl Crow. I really enjoyed that. But anyway, it doesn't matter. So one of the things that people have done since they realized that there were sunspots is first of all, in the mid 1800s, they discovered that sunspots come and go on the surface of the sun in a kind of a cyclical pattern. And you might have heard the 11-year sunspot cycle, maybe in your readings in your science secondary school curriculum. Well, almost as soon as people in the 1800s realized that the sun goes through these cycles, they began to wonder if these cycles weren't also reflected in other down-to-earth things. One of the things that they looked at first was agriculture and growing seasons, and whether in some places you had better results with some crops than others. And so they would plot them over time, and of course they wouldn't see anything. Then they looked at weather like severe lightning storms. Well, they didn't find any correlations with lightning storms in the 11-year sunspot cycle either. So, this whole idea kind of played itself out until, we started the 20th century, and then people didn't really look at those things. But they did try occasionally to find interesting correlations, but now the strategy was to be a bit more scientific. I mean, what you would do is understand why the sun has sunspots and what the impact that would have on the earth in terms of ultraviolet light and energy. And then you would look at various natural systems on the earth that might rely on solar energy in some way, and then look for the sunspot cycle reflected in those things. So one of the curious things that they looked at was on the stock market, there are some stocks that correlate with basically growing seasons, and some stocks that correlate with animal husbandry and beef production and stuff like that. I gave an example here of the price of corn on the stock market during this period, which is shown as a black curve. The actual sunspot cycle is shown in the red curve. And you can pretty easily convince yourself that there's no correlation between the two. Yeah, there's one that looks like it's in 1920 where they kind of go together, maybe 1930, possibly 1950. But the general trend is there is no correlation. They're just sort of random. Well, one thing that we'd like to do is, whether you have a detailed idea in mind for what things should be correlated with sunspots or not, maybe the first thing that you should do is, to see if your particular thing that you're interested in, lines up in time, with the sunspot cycle. That's a kind of innocuous thing to do. So what I decided to do is to, plot the data, the sunspot cycle versus the number of songs released each year in a particular way. Well, here's sunspot cycle counts by year. So you can see that, it comes and goes. Peaks and valleys are separated. The valleys are separated by 11 years. The peaks are separated by 11 years. It's 11-year sunspot cycle. All right. If you look at the number of songs that were released each year, you can get that number by, first of all, deciding that you're extremely bored tonight. You've got a couple of hours to spend on Google, and you basically Google songs on the sun with the sun in the title, and you do 1950, 1951, 1952, and you see what comes up on Google as a song that has sun in the title. Well, I did this, and I put the results in this spreadsheet, and I found about 100 songs between 1958 and 2008. Now, those are the 100 songs shown in the red dots. Well, it looks kind of interesting. The next question is, if we plot the two things together, we get this, but there's this caveat. If you look at the sunspot cycle, you'll see that the sunspots go up to a maximum between 150 and 200 spots. Well, 100 to 200 is sort of the maximum. But if you look at the songs, they go up to 6, and then that's it. So, okay, lesson number 1. These things are not correlated according to their amplitude. Songs are doing one thing in amplitude, and the sunspot cycle is doing something else in amplitude. So there's no easy scaling between 250 sunspots seen in one decade and the number of songs released in that decade. They're not related in that way. So what you do is what I did is to say, okay, forget about the details of the number of songs each year. Let's just take the information that shows how many were produced each year and multiply it by a factor of 30. What this does is it enhances the scale of the records, songs produced, to put it roughly on the same scale as the sunspot numbers. Now, I'm not going to use this to predict anything. All I'm trying to do is to take one kind of a data and overlay it on another kind of a data and stretch one or the other so that I can see more clearly whether or not they're correlated in sunspot cycle versus the period of the new data, or whether the minima or maxima line up. And so it's much more easier to do that, if you do this very simple manipulation. It also says that if we're going to do it this way, then we're going to forget all the information about the absolute number of songs produced each year. We're just not going to look at that as something that we're going to test for. But we will use the song data to tell us the general trend of each year, if there were more or fewer songs produced during those years. And we're going to compare that against the sunspot cycle. So if you look at it this way, let's see. What you can conclude from the sunspot cycle, which is the blue bars, and the songs, which is the red dots, is that, once again, we've got somewhere 1969, 1971, it looks like, the songs go through kind of a maximum at the same time that second cycle is going through a maximum. There seems to be a minimum 1963, but then it's a minimum for the entire 1950s when there's this huge sunspot cycle. So that's not a good thing. If you go to 1973, 1975, you see there's another big peak in the music, and the sunspot cycle is on the way down towards its minimum. Then 1981 to 1983, the music information fails completely to match the sunspot cycle there. And finally, 1989 through 1993, we have a major sunspot cycle there, and the records are simply going up slowly in numbers. And so just by eyeballing this, and this is at the level of beginning data analysis, just by eyeballing the data, you can conclude that there's no correlation between the number of records released or songs released each year and whether the sunspot cycle is high or low in intensity. So that's what you conclude using a simple analysis of the data. We can carry this a bit more aggressively and ask some specific questions, and this is sort of an intermediate level. Here we're looking for patterns a bit more specifically. First of all, we're asking the question, do the amplitudes match? Well, we already said no, they don't, because sunspots range between 0 and 190, and the song data is only between 0 and 6. So the ranges are not the same. Do the peaks and the valleys match up in time? Well, we already made the comment that they don't match up in time. There doesn't seem to be any relationship between whether you have a small number of records released and the sunspot cycle. So we conclude that there's no correlation between maxima and minima and the number of records produced. And finally, is there an overall trend in time? Well, the sunspot cycle has a cycle length of 11 years, and it's pretty regular. throughout the data. You can see the peaks and the valleys. When you look at the production of new records or new songs about the sun, you do find that there's a kind of a, it's low between 1955 and 1965, then it's high between 67 and 73, then it's low again between 77 and 1987, and then it starts going up high again, after that. So very, very crudely, it looks like the release of songs in the record industry between 1955 and 2008 has a very, very rough 20-year cycle. What does that mean? I don't know. It's certainly not the 11-year sunspot cycle. It's not even the 22-year hail cycle, which is also related to sunspots. So we can say that the data for the correlation between the two fails the trend test because the trends are completely different. So the assessment here is that the amplitudes are correlated? No, they're not. Are the peaks and valleys matching up? No, they're not. Do the overall trends match? No, they don't. And so the assessment would be that the songs released each year are not correlated with sunspot numbers. Now, that's something that we concluded at the beginning level of this webinar just by eyeballing the graph. I mean, we saw that they were basically doing different things. So that means that we are good if we plot things in a particular way that's comfortable to us. We're pretty good at seeing whether or not there are trends or not in data. But we want to be more precise than this. And what you do is a more thorough analysis of the data. And that's what we're going to do here in sort of the advanced level. As I said, the previous assessments were based on humans making a subjective judgment about trends. Okay, the judgments were accurate as far as we could tell, but we don't really know if they were accurate to within the errors in the data themselves. I mean, there actually might be a correlation lurking in there, but it's just that the noise is so high in the data that we actually don't see it very easily. That's why we have sophisticated statistical tests that let us probe the nature of the noise that's in the data. And if that noise doesn't look like what we expect for random noise, then we know that there's some additional information in the data. It might not be obvious to the eye, but there's clearly something else going on in the data that we need to probably understand. And I said, the huge match between the ranges of the two things being compared and hide actual correlation between them in the face of natural sampling variation. So that's why, we, as we say, we renormalized the song data so that it was on roughly the same scale as the annual sunspot number data to help us out with that. What we're going to do now, well, as I said, we concluded the amplitude not correlated. So that lets us do anything that we want to the amplitude data in the song data, so long as we do it the same way for each and every point. So if I take the 1 year's data and multiply it by 10, I have to take the second year's data, multiply it by 10. I have to take the 10th year's data, multiply it by 10, all across the board with the same multiplier, all right? That puts the song data on a scale that's, in this case, similar to what we have with the sunspot data. But what I'm also going to do is I'm going to look at the highest value that I see in the sunspot data, which was in year number 3, take that number and divide it into all of the other data. So that big point is going to have a value of 1.0, and any other data, any other amplitude data for that sunspot cycle is going to have a number less than that, but greater than 0. So essentially, I've taken the range of these sunspot numbers from 0 to 190, and I've converted it into a range that goes from 0 to 1. I do the exact same thing to the song data. There were 7 songs in 1 year as the maximum, so I'm going to divide all the song data for the individual years by 7, so that the song data is also put on the same scale that goes from 0 to 1.0. And that's what this plot shows. This now lets us, first of all, forget about the amplitude as being something we're going to test for. Instead, we're going to test for are the trends, whether or not the peaks line up, whether or not the valleys line up, and something about the period of the two series. Those are things we can look at now that we've taken the actual amplitude data out of the query. And so here we had this data. We also are going to subtract the average value of the data for each set from the value in each year. That puts the data, instead of going from 0 to 1, we're now going from -1 to +1. So it's more of looking at for each year how the song data is behaving relative to the sunspot numbers, where it could either be in advance or behind, depending on the sign. All right. So that's what I'm going to do here. And so you get that kind of a plot. And now what we're going to do is to see if there's a relationship between the series now that we've normalized them in this particular way. And the thing is that as you see this data here, both of the series seem to have like a lot of noise in them, although the sunspot data, you can clearly see that it still has this 11-year cycle to it. But the music data, it doesn't seem to have nearly the same kind of cycle at all. I mean, it seems, especially after year 10, it almost looks random to the eye. It goes above and below 0 roughly just as often relative to the average value of the series. So what we're going to do is we're going to assume that the sunspot cycle data is fixed. We're going to look at the song values for each year, but we're going to compare the difference between the sunspot number data and the song values for each year, take the difference. We're going to compute the standard deviation of this difference and then plot the frequency distribution. We'll compare the two, or what this distribution looks like. And then we're going to determine whether the difference we see are statistically significant. So it's a kind of a multi-step thing that we have to do. And here's roughly how we do it. We calculate the standard deviation of the mutual data, which is the songs and the sunspot numbers, subtracted from each other. We calculate first variance for the 52 points, and then we calculate the standard deviation, which is the square root of the variance divided by the number of degrees of freedom, which, because we've subtracted the average from the data, we have one less degree of freedom than we actually have 52 points. So that's why we get 51. All right, the average is 0. That's because we subtracted the means from each of the two zeros. So therefore, if you take the mean from one, subtracting the mean of the other, you're going to get 0, no matter what you do. We can now plot a histogram of the differences, and we see that it kind of looks like this. I note the standard deviation. We calculated the standard deviation, which was 0.41 at this step. And if we look at where that standard deviation falls, the data to either side of 0, which is the 0 difference, which is the average, you can see that at one standard deviation, it sort of takes up most of the data in our sample. Okay, we can be a little bit more specific about that. If we look at just a random process like flipping a coin hundreds of times and counting the number of heads and tails, or doing something else, we get a specific kind of a curve called the Gaussian curve. And it has the property that it has a mean of 0. Okay, we took our data and converted it into something which has a mean of 0 for the differences. We also calculated a standard deviation. So 1 sigma is 1 standard deviation, 2 sigmas is 2, and so forth. In our case, the standard deviation was 0.41. So that central part goes from -0.4 to +0.4. And if you add 34.1 and 34.1 together, you get, let's see, looks like 68.2. So 68.2% of the time, if this is a random set of differences between series, you should see most of the data points lining up within that peak. Now, it's kind of hard to look at this and to keep converting between our standard deviation of 0.4 and this plot. So what I've done is to essentially divide the differences, each of the 52 differences, by 0.41. That way, we're looking at the difference in relationship to the standard deviation. So if the difference in this case is 2, that means that that point is 2 standard deviations, or 0.42, away from 0, and so forth. So the top curve is what we get when we take the differences and divide by the standard deviation. We get that curve. That's an actual data curve. And now we can directly compare it with the Gaussian curve down below. And the differences divided by the standard deviation, that axis on the top graph is -1 standard deviation, -2, -3, and also in the positive direction, it's 1, 2, 3. So that matches exactly this Gaussian curve down below. And what we see is that essentially all of the data, all of the differences that we calculate between the sunspot numbers and the music produced fits within this Gaussian curve all the way out to 3 sigma. So 100% of the data points go from -3 to +3 in the top scale. So what that means, it means the following. It means that our data, the differences that we see in the data, are consistent with basically just random sampling errors and are not statistically significant. And you can translate that into hypothesis testing. Usually we state a null hypothesis. In this case, it would be there is no correlation between the sunspot numbers and the music releases. And what the similarity between these two curves tells us is that we can reject that null hypothesis at 99.6% confidence. And that means that there is no correlation between these two. The null hypothesis, I'm sorry, is that there is a correlation between these two. But we found that basically the errors that we see here, 99.6% of these errors are within the expectation for Gaussian noise. So this is how one says that you can reject a hypothesis to some particular level of confidence. And that level of confidence is determined by how much of the actual data is within 1, 2, or 3 sigma of this mean, and compared to what you should expect if it's random noise. We can also use an actual student's t-test calculator, which you can find online. I use this one, and what you do is it has a window which lets you put in the values for one series, and it has another window for the second series. And then it goes ahead and calculates what the statistical significance is of these two series, given the hypothesis that the null hypothesis that the data are correlated. And what it comes up with from the actual data is that that null hypothesis can be rejected with a confidence greater than 99.6. Basically what we calculated before doing a more, manual sort of analysis of this thing. So we have 3 different methods. We have, 2 methods that rely on you looking at things by eye and deciding whether or not they're related or not. And then we have a method which relies on a more careful calculation that looks at averages and standard deviations of differences and compares those against pure noise, Gaussian noise. And then we have a final version of this where we actually plug in the numbers on an online. This is called a student's t-test calculator, and it's a particular kind of a test that's called a one-tailed distribution. Because the original data were always between 0 and 1. All right, so that's one-sided. There were no negatives in this particular series. So anyway, we have 3 different methods, but then there's always a 4th method. We can asked ChatGPT to look at these two series.
Stan,
Yes.
this is Hillary. Before you do this slide, when you turn your head to the left, you seem to cut out a little bit. So I'm not sure why that's going on, but I just thought I'd mention it before you keep going.
Oh, okay.
Okay.
All right. So anyway, if you plug the two series into ChatGPT and ask a specific question, use a one-sided student t-test to determine whether to accept or reject the null hypothesis that the two series are correlated. Show your work. All right. So I'm asking ChatGPT to actually show me what it did and then tell me what the answer is. Well, here's where things got very crazy. All right. It gave me the average of the number of spots as 26.52 divided by 60. Well, that's wrong because there are only 52 spots. There are only 52 elements in the vector. I asked it to do the same thing for the number of songs. And again, it said that there were 60 elements in the average, but there's only 52. It then computed the t-statistic for 58 degrees of freedom. And this is wrong because it should be 51. And then it went on and on and on and came to the conclusion that there is sufficient evidence to suggest that the sequence of spots and songs are correlated. Well, all right, that's kind of hallucinatory. And for those of you that have played around with ChatGPT, you know that it hallucinates. I put in the 52 values for the spots by hand into ChatGPT, and I asked it to count the number of elements in the spot array and show me the count index opposite the number that you're averaging. And it went through, 1, and it gave me the number, 2, gave me the number, 3, gave me the number, 52 gave me the number, and then that was it. And then it said there are 52 elements in this array. So it clearly knows how to count the number of elements in the array. And clearly I entered the array accurately. There were no, 8 additional numbers that were hidden somehow in the way that I typed the array into the question bar. So I don't know what the heck ChatGPT was doing, but curiously, after it said that there were 52 elements in the array, I told it to once again calculate using the student t-test, what the confidence was. And it went through the steps, but this time it got lost in a loop. It kept giving me like the same line over and over again. And so clearly I had broken ChatGPT on this kind of a question. So the moral of the story is you can use ChatGPT, and we've seen this before in the previous webinars that I've given. You can use ChatGPT to plug in a number to an equation and turn the crank. All right. It's an intelligent calculator that way. Kind of like, the calculators you used in high school, in your math class where you entered the numbers into an array and you told it to compute an average. It can do that. Or it can evaluate a function at a particular value. It can also do some interesting calculus problems, all right, and get the right equation at the end. But for some reason, there are other kinds of problems that it seems to fail at, and this is one. This should be a very straightforward problem to do. But somehow it got lost at step 1, which involved calculating the average of 52 elements and trying to convince me there were 60 elements. So the point is, don't use ChatGPT to do statistical testing, at least in this case. Better to use an online calculator. There are several of those available. And so that's sort of where we wind up. So anyway, next time, we're going to be exploring, the theme is physical and mental health. Well, you've got to be an Einstein to figure out what the heck the connection between the sun and mental health is going to be in a way that highlights what the sun does. Well, you can talk about seasonal affective disorder and how the human requires a certain amount of light to keep its diurnal clock correlated. But here's another problem that I think is even more interesting. It's called everybody is into counting the number of steps they take every day to determine whether or not they're healthy or not. Well, we can do the same thing with the sun, except in this case, we're going to do the random walk problem going from the inside of the sun out to the surface and see basically how long it takes light to travel from the core of the sun out to the surface. And then 8.5 minutes, of course, it gets to the Earth. But so we're going to use the random walk problem, which is a mathematical problem, to figure out the age of sunlight. Well, that's sort of it. And so I'm going to stop sharing at this point. And if you have any questions.